Okay, here we are, 8.2b. We're on example 2, cost minimization. All right, so we've got this company that can make two different types of Blu-ray players. Okay, and they're making these Blu-ray players at two different plants. Plant 1 can make 60 units per hour of the Star model, and they can make 80 per hour of the Pro Star. Okay, plant number 2. A little bit bigger it looks like. They can make 300 per hour of the Star and 80 per hour of the Pro Star. Okay, so they've gotten this big order. They need 5,400 Blu-ray player of the Star, and they need 4,000 of the Pro Star. Okay, if it costs $2,000 an hour to run the plant 1, and it costs $3,000 per hour to run plant 2, all right, how many hours should each plant spend on manufacturing to minimize its cost? Okay, very, very important. They don't necessarily want this plant here to run all of these Blu-ray players because it costs them $3,000 an hour. It costs them quite a bit more to build the product here than it does over here. Yet, the Pro Stars cost the same to make, okay, $80 an hour. Or, I mean, they can make the same number. So this might be cheaper because they can make the same amount down here for this amount. But they can't make as many of these Star models because they can only make 60 an hour for the 2,000, whereas here they can make 5 times as many, but it only costs them $3,000 an hour to make 5 times as many as the one up here. So what we're trying to do is figure out how many from each plant we should make in order to have it cost the plants the least amount of money to make the product. Okay, the less it costs them to make the product, the more money they're going to end up making. Okay, so we're trying to make 5,400 Star models and 4,000 Pro Star. All right, so let's see what we've got here. We really don't need all of this stuff anymore because we have the book, and it says here in the book, if we let X equal the number of hours of assembly line at plant 1, number of hours at plant 1. All right, and if we let Y equal the number of hours at plant 2. Okay, so the cost function we seek to minimize is, so the cost function, C equals 2,000 X plus 3,000 Y. The 2,000 is how much it costs per hour, and this is how many hours. This is how much it costs at plant 2 per hour. This is how many hours we're running. Okay, so what are the constraints here? The constraints are the Star model, 60x plus 300y is greater than or equal to 5,400. And what this is this is how many units we can make here in an hour at plant 1. That's why it's times x. Okay, number of hours at plant 1. Okay, so 60 times how many hours, and then we're going to plant 2. Okay, so that number has to be greater than or equal to 5,400. And the Pro Star model, we've got same thing, only how many they can make at plant 1 and at 2, because they can make the same amount, greater than or equal to 4,000. That's how many ProStar models we want. Okay? So the non-negative hours. Okay, so X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. Okay? Because we're talking number of hours there. All right, so let's go ahead and graph this. Let me get the picture of the graph up here. Okay, so here is the graph, and we've graphed this line here, and we've graphed this line here using the constraints that we had. Okay, so we are looking at up here as our possible region here, because we can't pick points in here because the blue line, we're looking at numbers above the blue line and above the red line. That means they have to work for both. These are below the blue line, above the red line. These are below both the blue line and the red line. Can't use any of those. We have no maximums here because these go on forever. We have no boundaries here. So my choices for minimum cost are here, here, and here. So at the point 0, 50, at the point 40, 10, and at the point 90, 0. So those are the three places that we're going to look at to see if this works. So we go back to our original formula, C equals X plus 3,000 Y. Oops. Okay, so when we put these numbers here, 0 and 50 in for X and Y here, we get a value of $150,000. Okay? That means that if we close plant 1 down, because that's what X equals, and just run plant 2 for 50 hours, that's how much it's going to cost us. Now let's say that we run plant 1 for 40 hours and we run plant 2 for 10 hours. It's going to cost us $110,000. Okay, and if we run plant 1 for 90 hours and we shut plant Y down completely, it's going to cost us $180,000. All right, so these three prices are the total costs that it's going to be to make both types of Blu-rays. 4,000 of the ProStar and 5,400 of the Star. So this tells you in real life situations which of these three are going to give you the best deal. Your boss is going to be a lot happier with you if you tell him, okay, we need to run the first plant for 40 hours and the second plant for 10 hours. It's going to cost us $110,000 to make the same product, whereas if we do this one, it's going to cost us $180,000. So you're saving the most money doing this. Okay, so that is in order to find the minimal cost. Now, example 3 is showing you how to find the maximum amount of profit. So let's look at this one and find out, as far as hot dogs are concerned, about being able to make the maximum amount of profit. Okay, so this is example 3, and I'm going to kind of push through this one a little bit quicker. We've got this meat packing company that makes 2 different types of hot dogs, regular and all beef. And each pound of all beef requires 0.8 pounds of beef, 0.2 pounds of spices. So 1 pound, 0.8 and 0.2. Each pound of regular hot dogs is 0.3 pounds of beef, 0.2 pounds of spices, and the rest being non-beef meat products, which is a little frightening. All right, so the company has at most 1,020 pounds of beef and has more than 500 pounds of spices. if the profit is 90 cents on each pound for all beef hot dogs and $1.20 on each pound of regular hot dogs, how many of each type should be produced to maximize the profit? Okay, so letting X be the number of pounds of all beef hot dogs and Y being the number of pounds of regular hot dogs. Notice that X and Y are usually representative of pounds or a number. Okay, so we seek to maximize the function of, and you should be able to write this, P, profit, equals 0.90x, 90 cents per package, times however many pounds we have, plus $1.20 per package, times however many pounds we have. Okay, so subject to these constraints. Okay, there's your two equations there, and your x is greater than 0, y is greater than 0, because both x and y have to do with number of pounds. Alright, so the graph of the system of inequalities is more easily found if the first two inequalities are solved for y. Actually, you can plug these two into your graphing calculator as is, but they're just switching it so that you're solving for y there. Okay, let's move this out of the way and bring up the graph. Alright, so you graph this guy and you get this. Notice, as far as the graph is concerned, what you've got here. You've got 1, 2, 3, 4 different corners here. Okay? Okay, so if we look at back to our original formula that they gave us, P equals 0.9x plus 1.2y. Okay, if we plug 0, 0 in there, we get a profit of 0. Alright, not going to do us any good. Probably am not interested in this being our maximum profit. Alright, so then we try this number here, these numbers here, and these numbers here, and see what we get. And when we do that, we find out that 0, 2,500, which is this one right here, will give us a profit of $3,000 compared to the smaller profit on the other two opportunities there. So if we use 2,500 pounds of regular hot dogs and do not make any all beef hot dogs, then we're going to maximize our profit. So why are we making all beef hot dogs? So anyway, that's it for example number 3. And we will stop there with 8.2, the example 4. Very similar to what we've done with examples 2 and 3, so you can look at that if you'd like. But as far as the test is concerned, I'm more interested in you being able to do examples 2 and 3 rather than example 4. So anyway, that's it for 8.2.